Good afternoon, my YouTube viewers. It's Crystal here. I'm just here making another video, doing another code review. And basically what this code review is, it's a spin-off of my previous code review, because my previous code review I was talking about climate change and then I was talking about Arima. But I was just thinking about it, because you've got the Arima model, which is auto-regressive integrated moving average. And then you've got exponential smoothing. And what I wanted to do is I wanted to conduct an experiment to see which is better in this context. Is it Arima or is it exponential smoothing? So I decided to use the holt method, because the holt deals with double exponential smoothing, but I also use simple exponential smoothing as well, just so I could compare the two. And so what I wanted to do is I wanted to review the code and then review the code and then talk about the two other models that I included in this program. So I wrote the program in Kaggle's Jupyter Notebook, and it's free. So that's a great thing. It's online and it's free, and all you have to do is log into Kaggle and then you can have access to that. And after I created the program in Kaggle, I put the description in the box just so give people an idea of what it was all about. So here's your description. Some say climate change is the biggest threat of our age, while others say it's a myth based on dodgy science. We are turning some of the data over to you so you can form your own view. Even more than with other data sets that Kaggle has featured, there's a huge amount of data cleaning and preparation that goes into putting together a long-time study of climate trends. Early data was collected by technicians using mercury thermometers, where any variation in the visit time impacted measurements. In the 1940s, the construction of airports caused many weather stations to be moved. In the 1980s, there was a move to electronic thermometers that are said to have a cooling bias. Okay, so we've got the problem statement. So after we created our program in the Jupyter Notebook, what we wanted to do is we wanted to import the libraries. So we're importing NumPy as NP, and what that does is that creates NumPy arrays, and it carries out numerical computations as well as linear algebra. We also imported pandas as PD, which that carries out data processing operations to include creating and maintaining datasets and also time-stamping data. We imported OS, which is part of the operating system, and it will go into the operating system and retrieve the CSV files that are saved in the directory. We imported statsmodels.api as SM, and basically that is the statistical library that also does time series analysis and forecasting that we're going to be using in this program. We imported matplotlib.pyplot as PLT, and basically what that is a graphics library, so it's going to plot the data points onto a graph. We imported Seaborn, which is a statistical graphics library, so it's a higher level graphics library that's written on the back of Matplotlib. And then we imported the warnings library, so we won't be getting messages about warnings, we'll just get the standard program. So after we imported the libraries, then what we want to do is we wanted to load our data sets, and we use the OS directory to load the data sets into the system. So you can see there's 1, 2, 3, 4, 5 data sets, but the only data set that I'm going to use is the one that says global temperatures. So after we've loaded the data sets, we want to read the files, but the only file that I'm going to look at is global temperatures. So we're going to use pandas to read the files. So temperatures equals pd.readcsv and then the file name. And so you can see here's the temperature. And the only two columns that I'm going to be working with are going to be the column that says DT and the column that says land average temperature. So we're going to create a time series. So as I said, the only columns we're going to be working with are the column that says DT and land average temperature. So we're going to create a new time series in this regard. TS equals temperatures, DT and land average temperature. And then we're going to date stamp the DT. TS DT equals PD to date time, TS DT. And then we're going to take DT and we're going to convert it to the index. So TS index equals TS DT. And then we don't need DT anymore because it's already in the index. So TS equals TS drop DT, axis equals 1. So now you can see the data frame that we've created. We've got the date timestamp as the index and the temperature as the land average temperature. So now we're just going to check some information about this data set that we've created. So we've got 3,192 entries from 1750-0101 to 2015-1201. And it's only got one column, which is land average temperature. Then we're going to check for null characters, ts.isNull.sum, and we've got 12 null variables that are going to have to be dealt with because you're not allowed to have any null variables in time series analysis. So I decided that the best way to deal with these null variables was to interpolate them, and that's a type of imputation where it is you're just filling in the blanks. That's what interpolate is. It's just filling in the blanks. So TS equals TS, land average temperature. Interpolate method equals linear TS. So we see that we've got that. So I probably could have done TS land average temperature, but I didn't. But it's a univariate time series. So I could have said land average temperature. In fact, I think I might. Gonna delete this. I don't know how that happened. See what happens. I'm gonna run it. Okay, so let's see what's happened. So we've got DT and then we've got land average temperature, which we didn't have a column name to begin with, but we went ahead and put a column name in there. We check our null characters. We don't have any null values anymore because we've interpolated them. And basically interpolate just means fill in the blank spaces, really. But it's a bit different, and I wanted to do it. That's the best way to do it if it's a time series. And then so we plotted the graph, and you can see since we've got so many values, all the graph is it's just a big blob. So you can't do much with that if it's a big blob. So I resampled the data. So we're going to be resampling the data on an annual basis. So rather than resampling the data on let's see what we had before, on a monthly basis, we're going to resample the data annually. So TS resample equals TS.resample A.mean. So what we're going to be doing is we're going to be taking the average temperature. So that's your average temperature. So this is a plot of the average temperature, and really, to be perfectly honest, if I had wanted to, I could just stop right there and say, well, yeah, we have global warming, the earth is getting hotter, because it's pretty obvious from the fact that there's an upward trend that the earth is getting warmer. But I decided I wanted to see this through to the bitter end. So we're going to carry on working with it and see what happens. First thing you notice about this is the fact it does have a trend, but it doesn't have any seasonality. And then here's a histogram of it. And so you see most of the highest temperature is between 8.5 and 8.75. But you have some temperatures in the 9 and the 9.5 range as well. Look at some statistics. So we've made a mistake here. Max row equals, so it says, I think I made a mistake, didn't I? See what happens. Let's try it. Let's give it another try. So that's not very good. Let's try it again. Let's see what happens if we take out the land average temperature. Okay, let's just keep it like this for the time being, because obviously when you try to do it as a row, it's just not working properly. And I did have to do a fair bit of work to get the IDX max and IDX min to work. So we'll go back to our statistics, and we had to go back to the other way of doing it because the statistics didn't work when we did it with the column. So max row equals TS resample dot IDX max axis equals 0. Print max row TS resample max row. So max row is 25, 12, 31, and then the max row temperature is 9.831. Let's just see what we've got here. Okay. So, and then the min row equals TS resample.IDX min axis equals 0. Print min row TS resample min row. So the minimum row was 1752, 1231, and it was 6.5. That was your mean. So 1752 was a cold year. We'll just put it that way. Now we're going to check for stationarity, and we're going to use the adjusted Dickey-Fuller test. And we're going to check the p-value, and the p-value is, if the p-value is lower than 0.05, then that means the time series is stationary. And because the p-value is higher than that, that means the time series isn't stationary. But we already knew that the time series wasn't stationary because it had a trend. We checked the seasonal component using Stats Model Seasonal Decompose, and this is also a Stats Models method as well. So it's an additive decompose. So we look at the signal, we look at the trend, so you can see that there is an upward trend. We look at the seasonal, there is no seasonal, and residual, it looks like there's lots of noise in there. So we split the data frame up into training and testing sets. The train length is 90% of TS resample. So train equals TS resample colon to train length, and test equals TS resample train length to the end. And train.shape, train.test.shape, we have to look at the shape of our training and test sets. So you see the training set has 239 rows and the test set has 27 rows. Now we check our mean and variance, and checking the mean and variance is another way of checking the stationarity of a time series. So we know that the time series isn't stationary because 1, we saw the trend, and then 2, the Dickey-Fuller test said that it was greater than 0, the p-value was greater than 0.05. But the difference between the mean and train and test is negative 1.12, and the difference between variance of train and test is 0.157. And then, so it's not stationary. Now we're going to analyze the test set. You can see that's the analysis of the test set. And now we're going to use the Arima model. That's autoregressive integrated moving average. Y train equals train values. Y test equals test values. And P values equals range 0 to 8. Q values equals range 0 to 8. And D values equals range 0 to 3. And then here's the for loop. This is the for loop that we're going to use to determine the best order, and the order is going to be PDQ. So P is for the autoregressive part, and Q is for the moving average part, and D is for differencing, and that's for the integrated part. And this is the code that you can use, but what shall I say? I remarked it all out because after you use it once and you get the optimal order to use, you don't need to use it anymore because you take the optimal order and it tells you what the optimal order is, and then you put that optimal order in the model and you don't need to use it anymore after that. So the optimal order, when I ran this section of the program, I got 0 to 1. So 0 means that you didn't have to do anything with the autoregressive part. 2 means that it was difference twice. And 1 means that you had to smooth it once with the moving average. And so we checked our AIC, and your AIC is 271. AIC is another metric that tells you how well the model fits, how well the data fit and train into the model. So we made a prediction, we predicted on our model, and this is what we got. So you can see that even when we predicted on the model, we had an upward trend going up there. So in order to get there we go again. It went all the way to the bottom. So test equals PD, data frame test. Y hat equals PD, data frame Y hat. And so now we're going to check our error messages. And I like errors. And I like to use RMSE. And generally, when you're doing competitions and things, that's generally the metric that they're going to use is RMSE. So MSC, that's mean squared error, equals NP dot square, brackets, NP dot subtract, brackets, test, comma, Y hat, brackets, dot mean brackets. And that's your MSC. And your RMSC is NP dot square root MSC. So I like dealing with the RMSC. So we've got an RMSC of 0.274905, which I think is okay. And then what we have to do is Y test equals blank brackets or empty brackets for Y in test, land average temperature, Y test dot append Y test, and here's your Y test. And then Y hat array is a empty array for Y and Y hat 0, Y hat array append Y, and then here's your Y hat array. And then we have created a data frame. So you can compare your actual values to your predicted values. So DF equals PD data frame, actual colon Y test, predicted colon Y hat array, index equals test index. So now you can take your predicted values and compare them to your actual values and see what you get. So now that was our Arima, and what I want to do for a second here is I want to write down my AIC. AIC is 271.813. So that's what we had for Arima. And now what we're going to do is we're going to do simple exponential smoothing. So Y train equals train values, Y test equals test values. And then we have what we have to do here is we have to determine the best alpha to use. So alpha equals, we're going to import stats models.tsa.holt winters import simple X smoothing. So alpha equals np dot arrange. 0 is the start, 1.05 is the stop, and it's 0.05 is the increments. And then this is a formula that you have to fill out to get the best range. And it gives you the formula, tells you 1. It gives you the best RMSE. So that's what we're going to stick with. So we put it into the model of simple exponential smoothing. And so our alpha is a 1. And optimize equals false. And then our AIC is -411. So that's unusual because on the Arima, the AIC was 271, but on this one, the AIC is -411. And I know that the least value the less value you have, the better it is. But I don't know how that relates to negative numbers. So I don't know if it's a negative number, if it's better than a positive number. That's something I'll have to research. and then y hat equals PD data frame, y test equals PD data frame y test, y hat equals PD data frame y hat, and now we're checking our error, and error is 0.318. So your error with simple exponential smoothing is more than your error with Arima. And so we take our data frame and we compare our actual values to our predicted values, so you can see what that is. And then we plotted it onto a graph, so you can see that the prediction doesn't look as nice on the SES, simple exponential smoothing, as it does Arima. And then what we're going to do is we're going to do the holt method, and the holt method is called double exponential smoothing. So from state models, tsa.holtwinters, import holt. We're going to fit the model. I said model equals holt y train, and I decided to make exponential true because we know that the time series isn't stationary. So I thought, well, maybe it's best to make it true. And so we have an AIC of -464, but we can try it false and see what happens, because the default is false. And so let's just try it. Let's just try it, see what happens when we make it false. I don't think it really, but when you make it false, your RMSC is less. Your RMSC is 0.395. And let's look at the graph. So it's negligible, but the RMSC is better if you make the exponential false than it is if you make it true, which I had made it true because I thought, well, yes, it's going to need exponential smoothing. And the AIC is -464. So really, so that's it. That's it for your comparison. We've taken and we have compared Arima with simple exponential smoothing and holt, which is double exponential smoothing. And Arima had an RMSC of 0.27 and an AIC of 271. Simple exponential smoothing had an RMSC of 0.318 and an AIC of -411. And let's see what the holt method had. Holt method had a -464. So I would say, me personally, I would say that the Arima model did the best, performed the best with this data set. But what you have to do is you have to, whenever you're performing a time series analysis, you shouldn't just stick with one model. You should try a few models and then pick the model that has the least noise and also the best AIC. But me personally, I would go with the least noise, the lowest error. And that's basically the way you do it. So in this particular instance, Arima outperformed simple exponential smoothing and the holt method, which is double exponential smoothing. And I didn't even try it on the Holt-Winters method. And the reason why I didn't try it on the Holt-Winters method is because this time series doesn't have any seasonal components, and the Holt-Winters method is triple exponential smoothing. So it smooths the trend and it also smooths the season. And since this time series didn't have any seasonality, I didn't really see the point in using holt winters. But if you wanted to, you can always try the holt winters as well. But Arima won the competition. And so what you want to do if you want to save this, I found this out the hard way. If you want to experiment, you have to put it on quick save. Because if you don't put it on quick save, then it will fail when you try to save it. And that was something that I sort of figured out on my own. So if you decide that you want to use this data set, which is on Kaggle, by the way, and you want to experiment, then you need to use quick save. It won't, for me personally, it failed when I tried to use the normal saving route. So let's just see if it saves it. It saved it. It didn't save it when I did the normal saving route. So I'm going to go ahead and conclude this video. I would like to thank all my subscribers for supporting my channel. If you like this video, please like, subscribe, and share. And I look forward to making more videos for you in the future. So thank you very much for watching this video.